Good morning, everyone. My name is Dave Whiteley. I'm Technical Director of Envisage UK Limited, and this webinar is we'll be running through Autodesk Simulation 2013, and part of that is the mechanical event simulation software, and we're going to be doing two simulations today. One is of a 2D seal closure, and the other one is of a 3D container drop test. You often check a design while it is moving in a dynamic event, such as buckling, swinging, rotation or oscillation. Mechanical event simulation combines kinematic, rigid and flexible body dynamics and nonlinear stress analysis capabilities. As a result, MES can simultaneously analyse mechanical events involving large deformations, nonlinear material properties, kinematic motion and forces caused by that motion, and then predicting stresses. It's used a lot for doing an analysis to replace initial expensive tooling or mechanical similar on the real world designs. And the idea of MES is that we can actually analyze these large deformations and stresses in the software before we start paying out on expensive tooling. To that end, we'll just run through the software. I'm going to start off by opening a 2D drawing, an AutoCAD drawing of our seal assembly. Now, when you work with a 2D drawing and you bring this into the simulation software, it's important to note a number of things. First of all, in the drawing itself, in the AutoCAD drawing, if you place the geometry for separate parts into blocks, then when we import those into the simulation software, those blocks are imported as separate parts as per the yes/no box down the bottom here. We're importing wireframe geometry in 2D. It goes to the YZ plane for 2D elements within Inventor simulation with Autodesk simulation software. So these are the settings that we need to change for bringing in an AutoCAD drawing into the software. So we'll open that up. And we'll accept the units. And in this case, and in both simulations, we're going to select the MES with nonlinear material models. This will bring the 2D drawing into the software. We'll just look at the right view here. And I'll just collapse all the children for the parts. At last, in the software, we've got the ability to expand and collapse children within the browser here on the left-hand side. I don't need the drawing sheet. I don't need the ANSI frame. I don't need the flange top view. So we can actually suppress those and turn their visibility off. So we've now just got the geometry of the flange assembly, where we've got an O-ring part, the flange base, and the flange lid. Okay, we now mesh these. If you've got an analysis that is axisymmetric or symmetric of any sort, it's much easier and quicker to actually analyze it in 2D. It's faster, gives quicker results, and also it's easier to create 2D geometry in certain instances to do the analysis on. I'm just going to select the sketch planes for the geometry, and we'll create a 2D mesh using the default settings on these parts. Okay, this has meshed the 2D profiles for us. We've now got 3 parts meshed. We just need to change the element definitions for, as you can see in the browser here, there's certain inputs that are still required in red. So we'll just go through and change the element definitions here. All we've got to say is that the geometry type is axisymmetric. And also with MES software, the MES analysis, it's important that the analysis type is set to large displacement. Okay, so the materials, we've got the flange base and the flange lid, so we'll put those in. We'll make these steel. And for the O-ring, we're going to change the actual element definition, and we're going to use a Mooney-Rivlin definition here, which enables us to input our own stress strain curves for materials. And in this instance, I want to add from my library a rubber material which has got the stress strain data in it already. And then we need to define the boundary conditions. So we'll select the axis of rotation of this 2D profile, and we'll add a general constraint of Ty on this. In other words, this cannot translate in Y. This is a requirement for axisymmetric modelling. We'll select the bottom of the base here. We'll add a fixed constraint to that. And then we'll select the top surface. Now what I want to do here is I want to add a prescribed displacement. You can't add a prescribed displacement to surfaces. So now that I've selected the surface along the top here, I need to select sub-entities and select the vertices along the top of the mesh along here, and then I can actually add my prescribed displacement. Now the information I've got here is in inches, my units are in millimeters, so what I can actually do here is in the unit system within Autodesk Simulation, I can actually change the display units such that when I now select my sub-entities here and add my displacement, I can now put this in inches. This is in Z, and I have to put a negative magnitude in because plus Z is up. I want to move these, the prescribed displacement is down, so we add a negative value for the prescribed displacement, and then scalar Z is chosen. Okay, so that's the prescribed displacement. Now we need to define contact. So we'll just zoom in on these parts here. We'll choose parts for our selection criteria. And then using the control key, just select two parts. And then we'll add contact between these, surface contact. And the next pair, contact, surface contact again. We've now got at the bottom of the browser here two surface contacts defined. Now we can then go to the settings for these surface contacts. Okay, so this is a frictional contact. We put in our information for the frictional coefficients. And an important thing as well in the advanced button here is go to the geometry tab. And in this instance, we actually want to say that we don't want to extend the contact element sides between the parts. We want this just smooth because we've got all the geometry that we need between the O-ring and the groove of the component. So I don't want to extend any of these contact surfaces whatsoever. Okay, so we need to now just go to setup and go through our parameters for the analysis. It's changed in the latest release. We can actually input our time steps in different formats here. I want to put in here a capture rate. So I'm going to leave it at 1 second and put my capture rate to 25 frames per second. That gives us a total number of steps. We'll have a look at any load curves. The prescribed displacement is running on a load curve 1. We'll look at these more in the next analysis. But between time of 0 and 1 seconds, our multiplier goes from 0 to 1. So the multiplier is driving my displacement on the nodes on the top part of the assembly here, driving this down 1/4 of an inch from 0 to 1 times 1/4 of an inch between 0 and 1 second. Okay, we'll run the analysis. In this release, they've added the ability to show a convergence plot. Before you were just shown a log, as you see here, but if we go to the convergence plot, this gives us a plot of the number of iterations to convergence along the horizontal here. And if we minimize this and take a look, we're on time step 14 at the moment of 25. But whilst it's doing the analysis, we can actually look at what the results we've got so far. So we're in displacement here at the moment. So if I just take off the loads and constraints, even though it's a time step of 14 out of 25 at the moment, I can still run through, because I've got automatic advance on here, it will automatically advance on to the next step. But I can actually look at these, step through these analysis steps, or run an animation up until the analysis that we have so far. And if we just go to the stress. The other thing that you might want to do is change the settings for the legend. So instead of having a calculated range for the high and low values in the legend here, we could actually put in the values ourselves. So if I'm only interested in starting at, say 500 psi here, and then go up to 1000, then it gives us better results in the areas that we are interested in. And the other thing that you may want to do, because this is an axisymmetric analysis, is if we just right click on the parts here, we can actually put 3D visualization on, and that will then rotationally alter the model so we can see it in 3D. Just turn off the visibility of the lid. So here we've got the rubber ring, the rubber O-ring is compressing as the lid pushes down. Let's just take this symmetric off. So we've got non-linear analysis taking place. So we can analyse things like displacement of materials, stresses in parts in this mechanical event simulation. Okay, we'll now move on to the next one, which is the drop test. Here we've got a flatbed trailer with a container on it, and what I want to analyse, just wait for the model to open up. What I want to analyse is we're going to lift the container and swing it away from the truck, but then we're going to analyse the container dropping as it's so many feet, this is an imperial model, so many feet away from the trailer, and see what happens to the stresses in the container itself. So we're going to be analysing this. Now, when performing a contact analysis in MES with parts that start in contact, which they do here, it is found to be beneficial to define the contact pairs prior to meshing. Defining the contact pairs first will prevent mesh matching that occurs between mated parts during the meshing process. The mismatching of mesh in the contact pairs will improve solution convergence and improve runtime. So we're going to add the surface contacts before we actually mesh this model. I've got some done already. So for instance, we need to really decide what we want to analyze here. You can't, you could take all the parts and say do surface contact between all these parts, but to be honest that would take a long time to analyze. what we need to do is use our engineering knowledge of this and say, well, we know that the bottom of this container is going to possibly come into contact with the flatbed trailer. It may well come into contact with the wheels. We certainly know that the frames at the bottom of the container will hit the concrete base. So we add those surface contacts in. So just to finish this off, I'm just going to go to part selection and select the steel framework at the bottom of the container, and with the control key select the flatbed as well, and tell it that I've actually got contact between these parts. And we'll do this 3 times between the 3 different steel sections running along the length of the container. And the final one. Okay, that adds it to the contact list here, but be careful because it's added this as default. Now the default contact is bonded. We don't want these 2 bonded. We want surface contact between these, so we need to make sure that we select these contacts here and change them to surface contact. Okay, so let's start setting up mesh options here. So for the actual aluminium frame of the container, I'm going to change the mesh options for this part and tell it this is actually a plate stroke shell mesh type. And I'm also going to override the mesh size for this to be 5 inches. We're also going to take the ground and override the mesh settings for this, and we're going to put in a larger mesh size for the ground. And then finally we just go to mesh and we'll just change the setting in mesh here, and then we can go ahead and mesh the model. The software gives us a little bit more visual feedback on meshing now than it used to. We've got the ability to show the only the parts in progress on the list here. If you've got many parts being meshed, we can just show the mesh in progress. As they go green, the meshing is obviously finished. We can show details on the right hand side here as well. Okay, so that'll just generate the graphics for us, and then we'll have the meshed model. Now we need to define the element information and materials. Now I'm going to use a particular element on part of this design, which is called 3D kinematic elements, and I'm going to add these to the part of the truck that I'm in. I'm not interested in doing a stress analysis on, but I do need to make sure that the materials and the loads applied to them are experienced in this analysis. So when we change things like the truck cab, for instance, to a 3D kinematic element, these do not experience strains and they therefore do not report stresses. Otherwise these elements behave just like brick elements. They can have mass, loads applied on their nodes and or faces and experience motion. Their advantage over flexible brick elements is that they barely contribute to the size of the global stiffness matrix in the analysis. So we'll select everything up to the cab, and the element type we will change from brick element to 3D kinematic. This will also speed up the analysis. So even though these don't report stresses and strains, we can actually still add a material to these. So I'm going to go ahead and define the material for these 3D kinematic elements, and we'll make these steel. We'll then select the other steel components in our analysis and just change those as well. The shelter, we need to edit the element definition first because this is a shell element. We need to give it a thickness. So until we can give it a thickness, we can't change the material. So we've given it a thickness. We can now give it a material, which is aluminium in this case. And then finally we'll take the ground and edit the material and change that to concrete. Okay, so that's everything there defined. We now need to define our loads and boundary conditions. Now again, as we did with the last analysis, we need to select nodes to add a movement to. So I'm just going to select vertices and just select the 3 vertices on the corner of the top of the container, and then add our prescribed displacements to these. So first of all, we're going to move this to the left of the trailer, which is in the negative Y direction. So we use scalar Y for our direction, and because this needs to be negative, because it's opposite, it's negative Y, we'll put in a negative value, 60 inches. And then we'll start using load curves. I'm going to leave load curve to 1 alone. I'm going to use that for gravity later on. So I just need to put this to load curve 2. And the idea of load curves is actually we can drive this displacement. So if I just add a few rows here, my duration of this analysis is going to be 8 seconds. After 2 seconds and after 5 seconds, we're going to be doing something different. So this is how it's going to work. If I just put 1 in for here and here, this is a multiplier of the displacement of my minus 60 inches. So between 0 and 2 seconds, it's not going to move. And then between 2 and 5 seconds, it's going to move from 0 to minus 60 inches. And then from 5 to 8 seconds, it's going to stay where it is, right? Okay, then we're going to have a look at this active range. We're only going to use curve number 1. And in here, we're going to give it a depth time of 5 seconds. Now we've got an 8-second simulation. But I'm going to actually have a depth time on the prescribed motion of 5 seconds. So what's actually going to happen is that defining this depth time will release the prescribed displacements and allow the container to move freely. So between 5 and 8 seconds, it's going to be falling under gravity. With the point still selected, I'm going to add another set of prescribed displacements because we need to move this up. And I'm going to move this up in Z, 12 inches, and we're going to use curve 3 this time. So we'll add some more rows to the curve, again to 5 and 8 seconds. And this time, what's going to happen is between 0 and 2 seconds, we're going to lift it up from 0 to 12 inches. It's going to stay at 12 inches between 2 and 5. And then because we've got a depth time of 5 seconds, it's going to drop from then on due to gravity. So there's our prescribed displacements from the model. And finally, we need a fixed constraint on the surface at the bottom here. And our model is ready to analyze. So what we want to do now is we want to lift the container up for 2 seconds, swing it across, and then let it drop. So we need to go to our setup here in the model parameters. We need to tell the analysis that we're going to run for 8 seconds. The capture rate is going to be, say, 20 frames a second. That gives us a total of 160 steps it's going to analyze for. And remember earlier I said we're going to leave load curve 1 for gravity. So we're going to go to our gravity tab here and set for standard gravity, which by default will use load curve number 1. And in our load curves here, we must make sure that we leave the multiplier at 1 for the whole duration of the analysis. We don't want gravity changing. Okay, on that we're ready to run. Now this analysis takes about an hour to simulate. There's a lot of analysis going on here. So what I've got is the video that is produced from this analysis to show you what actually happens. So we lift it up by 12 inches, swing it across. It then drops at 5 seconds, and for then the next 3 seconds we can actually animate and analyze actually what's happening to this container. Good things to do would be to change the legend properties again, to put in there the actual values that you're interested in analysing. In the software you have the ability to actually produce a report of the maximum results summary, which enables you to show where maximum results are per step in the analysis and on what parts and nodes of that part the maximum results are being obtained. So we can get lots of results from this, and obviously this is a lot cheaper than running a physical simulation, whether it's a plastic mould or a plastic part assembly clipping together, drop tests and so forth, where these are very costly to take place and to analyse in the physical way, whereas with the MES software we can actually run this mechanical event simulation and produce real-time and real-world results on linear and non-linear materials. So thank you very much for attending. Please take a look at our YouTube channel, Envisage UK Ltd, where we have more videos. Any contact details you want to get into contact with me, then please contact me on the details on the screen. And thank you very much for attending.